Hello everyone, welcome to this video. In this video, we are going to discuss about direct volume data rendering by the help of this PPT. So let us see what are the topics we will cover in this video. First, we will start with introduction to volume rendering. Then we will learn about basic concepts of DVR. Then we will see ray casting, which is an important aspect in DVR. Then we will move towards transfer functions in DVR, applications of DVR, challenges in direct volume rendering, modern trends in direct volume rendering, future directions in direct volume rendering. Then further about we will cover summary and references which were used to make this PPT. So now let us see what is the objective behind this PPT. The objective is to understand the concept and importance of direct volume data rendering in visualizing the 3D datasets. This is widely used in computer graphics, and we will see the techniques by which we can explore and tools used for rendering volumetric data directly to analyze the performance, interactivity, and applications of direct volume data rendering in various fields. So first of all, let's start with Introduction to volume rendering. So volume rendering is a technique for visualizing 3D volumetric data. Unlike traditional 3D graphics, which represent surfaces explicitly as polygon, volume rendering directly visualizes data that exists in 3D space, such as density, temperature, or intensity. Volume rendering is used in various fields. It is also used in fluid dynamics. It is widely used in medical science for capturing the images via MRI and CT scans. It is also used for realistic renderings of clouds and weather modeling. So now let's see what are the basic concepts of DVR. Direct volume rendering is a visualization technique that generates images directly from data without converting it into surface geometry. Ray casting is an important feature of this, in which a ray is sent from the eye into the volume. It samples data along the ray path. We will discuss ray casting in upcoming slides. Color and opacity are computed at each sample point in ray casting. So now let's understand ray casting in depth. Ray casting is a key method in direct volume rendering where rays are projected from the viewer's eye through each pixel in volume. As the ray travels through the 3D data, its sample value at regular intervals. These values are converted into color and opacities using a transfer function. We will also understand transfer function in upcoming slides. The resulting sample are then combined using a compositing techniques to produce the final image pixel, enhancing with shaded to add depth. Here is a diagram shown for ray casting where we can see a camera, image ray, light source, shadow ray, and scene object. So some key points regarding ray casting. A ray is cast through each pixel into the volume. See here another diagram is shown where it is the ray is passed through each pixel. Scalar values are sampled at interval along the ray. Transfer function maps values to color and opacity. Optional Optional shading adds lightning effect using gradients. Compositing blends samples to form the final pixel image. Now let's understand about transfer function in DVR. A transfer function is a key component in direct volume rendering that maps scalar values into the volume data to visual properties like color and opacities. Now let's see what is the purpose of transfer function. It converts voxel values into RGBA, red, green, blue, alpha for visualization. There are different types of transfer function listed as here: 1D transfer function and 2D transfer function. The one-dimensional transfer function is based on the voxel scalar value only, whereas the 2D scalar function is based on scalar value and gradient magnitude, which helps to emphasize edges and surfaces. Here, user control is also present, like customization to isolate and emphasize regions of interest. Now, let's see what are the applications of direct volume rendering. It is in today's time, direct volume rendering is widely used in the field where internal structure of 3D data needs to be visualized without extracting surfaces. It is widely used in medical imaging to help visualize organ, bone, and tissue from CT or MRI scans. Now let's see the key applications. As listed, the first application is medical imaging, that is visualizing CT and MRI scans for diagnosis and surgery planning. Second is for scientific research, analyzing fluid dynamics, astrophysical simulation, and weather data. It is also used in geophysics to interpret seismic volume of oil and gas exploration. In engineering also for viewing simulation data like stress, temperature distribution inside the object, it is widely used. Now let's see about challenges in direct volume rendering. First is high computational cost. Real-time rendering is demanding due to heavy sampling and composition operations. Transfer function design. Mapping data to color opacity is non-trivial and often requires expert tuning. Visual clutter. Dense data can obscure key structure, making interpretation difficult. Memory uses. Large dataset consumes sustainable GPU and CPU memory, limiting scalability. Interaction limitation. Real-time manipulation, zoom, rotate, filter is hard with high volume. We cannot use these functions for a very large volume of data. The last point is lighting and shading complexity. Accurate simulation of light when volumetric data is computationally expensive. Moving further, we will study about modern trends in direct volume rendering. Modern advancements in direct volume rendering focuses on improving performance, visual quality, and user interactivity. With the rise of GPU computing, data volume rendering can now achieve real-time rendering for large datasets. New approaches also integrate machine learning for transfer function design and employ web technologies for broader accessibility. Like GPU acceleration, real-time DVR using graphics shaders, GLSL, CUDA, OpenCL for faster processing. Second is deep learning assistance. AI model help automate transfer function generation and feature segmentation. Web-based volume rendering, use of WebGL and JavaScript libraries for browser-based visualization. Now let's see what are the future direction in direct volume rendering. Now, as we know, with rise in technology, the data size is also growing. So, as data size grows and visualization demands more and become more complex, the future of direct volume rendering lies in making rendering faster, smarter, and more accessible and even cost effective. Emerging technologies like artificial intelligence, cloud computing, and immersive environments are expected to significantly enhance DVR's capability. Now let's understand what are the key features direction. The first one is AI driven visualization. Now with the help of deep learning to automate transfer function design, feature extraction and anomaly detection. Second is cloud based DVR, rendering large dataset remotely with high performance cloud computing accessible via thin client or web browsers. Scalable DVR for big data. Techniques for visualizing petabyte scale simulation or scan data using out of core and streaming methods. Now we are coming towards the end of our topic. So let's summarize this. DVR is a powerful method for visualizing 3D volume data. It enables insight into internal structure without surface extraction, key to many modern scientific and medical tools. It helps in many, as we studied in the application of DVR part, there are many applications of DVR like use of DVR for medical purpose, for engineering purpose. So now let's move ahead. Now these are the references which I use for making this PPT. I use my course notes and lecture material. I also refer to Wikipedia, Computer Graphics by Donald Hearn, Fundamental of Computer Graphics, and the last is Overview of Volume Rendering. I hope this video finds interesting for you and all the topics which are covered are clear to you. Thank you for watching this video.